We now come to the final section of Calc 1, and we are going to introduce and prove the fundamental theorem of calculus. So let me start by defining a definite integral. And then I'm going to state the fundamental theorem of calculus and do a quick example. And then in the next video we are going to prove the fundamental theorem of calculus. So, the definite integral here, let's say I have a function y is equal to f of x. And I'm interested in getting the area from A to B, the area underneath the curve, this shaded area here. So basically the definite integral is defined to be the shaded area underneath f of x. So the definite integral of f of x, so the definite integral of f of x from A to B is defined to be the shaded area. So the definite integral is a number, okay, and it's the shaded area, and is denoted by the following notation. You have an elongated s from A to B of f of x d of x. This is basically what we use to denote the indefinite integral, except there was no a and b. Okay, it was just an elongated s f of x d of x. Okay, that was the indefinite integral. When you put a and b on there, two numbers here representing the two endpoints of this interval, then you have a definite integral, and the definite integral is has a numerical answer, and it's equal to the area underneath the curve from a, or underneath f of x from A to B. So this is equal to the shaded area. So now we can finally see where this notation comes from. It comes from the Riemann sum. So if you remember, the area under the curve here, it was actually equal to the limit as the number of rectangles go to infinity. And you would sum up the area of all these rectangles, right? And so you would have k equals 1 to n. And so this gave you the height of each rectangle, and then delta x was the width of each rectangle. And as the number of rectangles go to infinity, this gave you the area of each rectangle, and then you summed them up, all in rectangles up, and then you got an approximate area. But if you take the limit as n goes to infinity, then you get the actual area. So in a sense, this is like taking the limit as n goes to infinity. So this elongated s, just like this is a Greek capital S in a Greek alphabet, this elongated s is kind of like the limit of the sum. So you have this sum, you elongate it, and now you have the limit as the number of rectangles goes to infinity. And these rectangles are going from A to B, so you put the A to B right there. And then this thing here is kind of like, that's where the f of x is coming from. This c of x is just some value inside the rectangle there. It could have been the lower endpoint, the upper endpoint, the midpoint, and technically it could be any number in there. Okay, so that's where this f of x is coming from the area. And then this delta x, as you let the delta x shrink down to 0, then it becomes a d of x, right? And so this f of x times d of x is kind of like the area of a single rectangle, and then this elongated s is that you're summing up all of those infinite rectangles that go from A to B, okay, and then you get the area. So this area then, this is equal to this definite integral. So this actual notation is coming from the Riemann sum. The elongated s because you're taking an infinite sum, and then this f of x times d of x because you're finding this is like represents the area of each of those rectangles. Okay? And so that's actually where that notation comes from. So now the fundamental theorem of calculus is what relates these together with the antiderivative. So let me finally state the fundamental theorem of calculus. So basically let f of x be a continuous function on AB and let capital F of x be its antiderivative such that basically if you take f prime of x, you're going to get f of x. Then we have the following. We have that this definite integral from a to b of f of x with respect to d of x is equal to capital F of b minus capital F of a. So this formula relates the area under the curve to the antiderivative, and it shows the actual relationship. So if you can find the antiderivative, if it has an antiderivative over the interval, then you just have to evaluate the derivative at the two endpoints of the interval and subtract them. The difference between those is actually the area underneath the curve, underneath f of x. And that's the relationship. And another way of thinking of this is this antiderivative here. This is like a rate of change function. This is like the total change. So the rate, if you want the area underneath the rate of change function from f of a to f of b, then it's equal to the total change between a and b. You can kind of think of it like that. Okay, so let me just do an example. What I'm going to do is I'm going to do, I can do, a couple examples. So first let me do this one. This is the one that we did initially, the initial sum. So I did 1 to 3 of x squared d of x. Okay, and if you remember, it's like 8.6 repeating. It was like 8 2/3 or whatever is what it was. And we actually used the infinite sums and got the exact value. I'm now going to use the fundamental theorem and get the exact value. So I just need the antiderivative of x squared. That's no problem. It's x cubed over 3. And so what I do is I write the antiderivative and then I say from 1 to 3. So this notation here means you're going to evaluate it at 3 and subtract. You'll evaluate it at 3 and 1 and subtract the 2. So it means place 3 into the antiderivative. So 3 cubed over 3 minus 1 cubed over 3. This is what it means. So you write the antiderivative, and then you put a line, you put the two limits, and then this is just placing this in there minus this in there. And then what I get here is that this 3 cubed is 3 times 3 times 3 is 27 thirds. Minus, this is 1/3. 1/3. And so I get 26 thirds. Well, 3 goes into 26 8 times with 2 left over. There you go. There's your 8 2/3. So it's that easy. So imagine all the work we did. Let's see if I can find it here. I don't know if I have it Do I have it? I might have put it away. Oh no, here. So all the work that we did was right here. There was x squared from 1 to 3. It took all of this. Oops. All of this. Let's see. Oh, so all of this onto this down to there, 26/3. And we got it just like that. That easy. Isn't that beautiful? That, my friend, is the fundamental theorem of calculus. And that's why it's so awesome. So it's very, very useful. So let's do the other one that we did. We did 0 to 1 of x cubed minus x d of x. This is the one that you did. Okay? And we'll use the fundamental theorem. So this, we can find the antiderivative. It would be x to the 4th over 4 minus, this one would be x squared over 2. And we're going to evaluate this from 0 to 1. Okay, so putting in 1 into this, I get 1/4 over 4 minus 1 squared over 2. So that's putting in 1, and then I'm going to subtract when I put in 0. And I'm going to write it out just so you see what I have to do, even though this is clearly going to be 0. 0 to the 4th over 4 minus 0 squared over 2. So this is it evaluated at 1. This is it evaluated at 0. And so I get, ends up being 1/4 minus 1/2. And we get a negative 1/4, which is exactly what we got when we did it using the limit of the Riemann sums. So there you go. That, my friend, is the fundamental theorem of calculus. In the next video, I'm going to attempt to give you a proof of it. So that's coming up next, and then we'll have several videos where we'll actually find the values of some definite integrals.